A block of high explosive detonates, transforming solid matter into expanding gas in a fraction of a millisecond, releasing a massive surge of energy. This is the spontaneity paradox. The fact that a chemical reaction is energetically favorable tells us nothing about how fast it will happen. Gibbs free energy, or delta G, is the thermodynamic rulebook. A negative delta G guarantees that a reaction can proceed without outside assistance. It dictates the starting point and the final destination. But delta G is entirely blind to the journey between those 2 points. It cannot tell you if that trip will take a millisecond or a millennium. To understand the speed of that journey, we have to look at the distinct set of rules governing reaction rates and mechanisms, which brings us to the entire field of chemical kinetics. Medical and advanced science exams actively exploit the overlap between these two fields. They present thermodynamic data to tempt you into making false kinetic assumptions. To predict reaction speed accurately, we have to decouple our thermodynamic assumptions from our kinetic realities by navigating around 4 persistent analytical traps. Mastering kinetics requires recognizing that macroscopic chemical equations are often just illusions, hiding a highly complex macro-reality. The first trap is assuming that a highly exergonic reaction, one with a large negative free energy change, will naturally proceed rapidly. For any reaction to occur, molecules must physically collide. They have to hit each other in the correct orientation and with enough kinetic energy to break their existing bonds. This is a reaction coordinate graph. It plots free energy against reaction progress. The line dropping from the high-energy reactants down to the low-energy products maps out an exergonic reaction. Before those molecules can reach that low-energy payoff, they have to climb an energy hill. At the peak, they form a temporary, highly unstable structure called the transition state. The energy required to reach this peak is the activation energy, or EA. This is the true kinetic bottleneck. A reaction's speed is dictated entirely by the height of this hill, regardless how far the energy levels drop afterward. Heating a system increases reaction speed because it gives a larger fraction of the molecules the kinetic energy required to scale this specific peak. A catalyst increases reaction speed through a single mechanism. It provides an alternate reaction pathway with a lower activation energy. Notice the graph. The starting energy of the reactants and the ending energy of the products remain exactly where they were. The catalyst only lowers the barrier between them. The kinetic bottleneck is governed entirely by the activation energy, a variable completely divorced from the thermodynamic destination. The second trap involves looking at an overall balanced equation and assuming its coefficients define the rate law. Consider this standard chemical equation. One molecule of A2 reacts with 2 molecules of B to produce 2 molecules of AB. For this to happen in a single step, 3 separate molecules would have to collide at the exact same location at the exact same microsecond with perfect orientation and energy. The physical probability of that is near 0. Instead, the reaction unfolds in a sequence of hidden microsteps. First, A2 collides with a single B to form A2B. Then that A2B collides with the second B to form the final products. The A2B molecule is an intermediate. It is created in the first step and immediately consumed in the second, so it never appears in the overall macroscopic equation. In any multi-step sequence like this, one of the individual collisions will take longer to occur than the rest. This slowest phase is the rate-determining step. It acts as an absolute speed limit for the entire chemical process. The final product can only form as fast as this specific bottleneck allows. Because of this, the true kinetic rate law is derived exclusively from the specific reactants colliding in this slow step, completely ignoring the overall balanced equation. The balanced equation provides the total inventory of ingredients. The hidden mechanism determines the speed. The third trap occurs when calculating that speed. It is easy to mistake the rate law for the law of mass action used to calculate chemical equilibrium. Equilibrium expressions factor in the concentrations of every species in the system, including the products. Rate laws measure forward speed, so they strictly calculate the concentration of the reactants. The fourth trap is treating the rate constant, K, as a universal static number. For any given reaction, K fluctuates depending on both the ambient temperature and the activation energy. Because of these hidden variables, there is only one guaranteed method to find an accurate rate law, deriving it from raw empirical data. This table displays an initial rate experiment. We have 3 separate trials showing the initial concentrations for reactants X and Y, alongside the resulting initial rate of product formation. To isolate the kinetic impact of a single reactant, we have to find 2 trials where all other variables are held constant. Look at trials 1 and 2. The concentration of reactant X remains exactly the same, but the concentration of reactant Y is doubled. While Y doubled, the initial rate of the reaction increased by a factor of 4. 2 raised to the power of 2 equals 4. Because the rate quadrupled when the concentration doubled, the reaction order with respect to Y must be squared. We repeat the process for reactant X using trials 2 and 3. Here, Y is held constant, X is doubled, and the initial rate strictly doubles. A 1-to-1 proportional change means the order with respect to X is 1. We plug those specific exponents back into our general equation alongside the rate constant, giving us a complete mathematically proven rate law. Reaction orders cannot be guessed by looking at the geometry of a molecule. They are strict mathematical realities extracted from physical evidence. Once we derive that overall rate order, it defines the specific geometry of how the reaction decays over time. In a 0th order reaction, the rate is entirely independent of reactant concentration. Pumping more reactant into the system does not speed anything up, a scenario commonly seen when a catalyst is fully saturated. This chart displays a 0th order reaction. Plotting the concentration of the reactant against time produces a perfectly linear, downward-sloping graph. A first-order reaction has a rate proportional to just one reactant. This suggests an event where a single molecule undergoes a change entirely on its own, like the radioactive decay of an isotope. Because the rate slows down as the reactant is depleted, the basic concentration curve is nonlinear. To linearize a first-order reaction, we plot the natural log of the concentration against time. A second-order reaction relies on a rate proportional to the concentration of 2 reactants, representing a physical process where 2 distinct particles must successfully collide. To linearize a second-order reaction, the mathematical signature requires plotting the inverse of the concentration against time, resulting in an upward-sloping line. True kinetic mastery requires ignoring the macroscopic illusion of the balanced equation. You must isolate the micromechanical bottleneck, navigate the physical reality of collisions, and rely entirely on the empirical data to prove the math.